Okay, so it turns out that there's a much more concise way of writing the sum of squares. So sum of squares, when you start talking about vectors, should actually immediately beg to use squared norm, right? Just like we had the chi-square, which was a squared norm, sum of square of the entries of a vector. This begs to be called the sum of squares of the entry of a vector. Okay, so if I want this to be the square norm of something, I need to have a vector that has entries yi. So that's easy. All I have to do is to stack up my yi's into one vector. And I need another vector that has entries xi transpose beta. But if I do this, this is basically a matrix multiplication problem, right? So if I take my xi transpose and I make them the rows of a matrix, and I hit it with a beta, each entry of the resulting vector will be of the form xi transpose beta. And so that's what the matrix form is doing for me. So first, I stack all my yi's into some boldface y for a vector. So now it's, of course, an n-dimensional vector, number of observations. And the way I'm going to stack my x's is by looking at the rows which are of the form x1 transpose, x2 transpose, x3 transpose, etc. And I'm going to stack them into some matrix X. So here I use this blackboard boldface. All right, so this is a matrix. What size is X? Yeah, n by? Yeah, n by p. Okay, there's n rows, x1 transpose, x2 transpose, all the way to xn transpose. Each of those guys is of length p. It's a vector in Rp. Okay, so now what I have is that I have this new model. So, okay, of course, I'm stacking up also my epsilons the same way I'm stacking up my y's. And so when I do this, now I'm going to have yi is x times beta, and this is a matrix product plus epsilon. Okay, so that's the new form of my problem, and if you actually try to represent it, this is what it's going to look like. So you have a vector that has your yi's, y1 to yn. So this is my boldface y. And it's going to be equal to my matrix. Sorry, I should not make it that long. That's okay, so this is the matrix blackboard X. Each row of this matrix here is x1 transpose, xn transpose. Then I multiply it by some beta star. Sorry, there's a star here. It's shorter again. Okay, so of course this is just beta 1 to beta p. And then I'm going to have plus my vector of epsilons, epsilon 1 to epsilon n. Okay, so this is just a compact way of saying everything you've read before on this previous slide, right? So this thing that says, oh, look at the first line, yi is xi transpose beta star plus epsilon I. All this is doing is just stacking all these equations like this, one on top of the other, and just combining everything into a matrix. Right now, it's just a notation trick. There's nothing to it. What's going to be useful is that this will allow us to actually use linear algebra now that we have a matrix to play with. So now when I write my least squares estimator, beta hat, remember this was actually the argmin of the sum from I equal 1 to n of yi minus xi transpose beta squared, which is exactly the squared norm of the distance between this guy and this guy. Agreed? It's just the sum of the square of the coefficients of this difference. Right, so here I use the fact that if I talk about the square norm of a vector, I don't know, w, this is just sum from I equal 1 to n of wi squared, if w is in Rn. Okay, so that's just notation. But then I'm going to be able to use matrix calculus. When I want to take the derivative, I'm going to be able to take derivative with respect to a whole vector, which is also known as a gradient. I'm going to set the gradient equal to 0. And matrix calculus is going to keep all my notation much nicer. I won't have to carry indices and crazy things like this. And so that's basically how we're going to do this. All right, so I'm going to stop here. And next time we'll move on to doing some inference when we're equipped with this by, for example, assuming that my noise is Gaussian.